Thanks to the presence of dislocations, I can cut this aluminium foil with a pair of scissors. This is because dislocations in the material enable us to slide the foil on one side of the blades against that on the other side. This electron micrograph shows dislocations in a crystal under very high magnification. They show up as these thin black lines. Under normal conditions, dislocations are the carriers of plastic deformation in crystalline materials. Whenever a plastic strain occurs, as in the foil where the scissors made contact with it, dislocations move. This diagram shows what happens in an electron microscope as the electron beam passes through a thin metal sample, about 0.1 of a micron thick. The dislocation goes through the sheet at an angle from top to bottom, but the beam of electrons is diffracted by the dislocation, producing a dark image. The dislocation image here has two ends. One corresponds to where the dislocation cuts the top surface of the sample, and the other corresponds to where it cuts the bottom. In our macroscopic world, examples of dislocations are hard to find, so to the newcomer, the concept may be hard to grasp. We hope that after watching this video, you'll have a clearer understanding of them. We're going to start off by considering an edge dislocation. Names are helpful here. The edge dislocation is so called because it lies along the edge of a plane of atoms or ions that terminates within the crystal. This diagram shows a cross-section through a crystal where the terminating plane of atoms can be seen edge on. It would be coming out of the crystal towards you in a straight line. This symbol is often used to represent a dislocation. In 3 dimensions, the dislocation is a line which follows the edge of the atomic plane here, where an extra half plane of atoms has been wedged into the crystal. This model represents the same situation that you've just seen in the diagram, but whereas the diagram was 3 atoms deep in this dimension, this model is only 1 atom deep. Each layer of balls in this model represents 1 layer of atoms. Into this layer of balls, we've introduced a magnet which attracts a magnet which is inserted into each ball in this layer above it. The attraction between those magnets imitates the chemical bonds between these pairs of atoms. Let's see what happens if we introduce a dislocation into our model. The dislocation's here. Keep your eyes on it and see what happens to it as we move the top layer of atoms relative to the bottom layer. The dislocation has rippled through from this side of the model to the far side, whilst at the same time individual atoms have only moved by 1 atomic spacing. Let's take a closer look at that, and to help you understand more clearly what's happening, we've slowed down the movement of the dislocation. As the top layer of atoms moves over the lower layer, the dislocation suddenly moves and slip occurs. This model, as I've said, is only 1 atom thick in this dimension, compared with many layers of atoms in a real crystal. In a real 3-dimensional crystal, the line of the dislocation lies along this direction here. When slip occurs, the dislocation moves along the slip plane. As you can see, before the dislocations move through the model, we have a straight line of atoms at the end of the model here. Let's see what happens if we move the dislocation through. Now a ledge has formed, and this is evidence that slip or shear has occurred because the top layer of atoms has been displaced by 1 atomic spacing relative to the bottom layer. Now let's do an experiment with our model. I'll start by resetting the atomic positions and introducing an edge dislocation. Here's our dislocation. And what we're going to do is measure the displacement of the top layer of atoms relative to the bottom layer that's necessary in order to move the dislocation through the model, thus causing slip. To help us measure that, I'm going to put this scale on the model here. So let's watch the needle to see how far we have to displace the model. That's a little over 2 centimeters. Now let's repeat the experiment, but this time without a dislocation being present initially. I'll just reset the scale. And again, I'll displace the top layer of atoms relative to the bottom layer. That was just over 7 centimeters worth of displacement that was needed. The difference between these two readings is significant. In the last case, when no dislocation was initially present, a much greater displacement was necessary. Can we relate this to the strength of real crystals? The movement or displacement required to cause slip is a measure of the shear strain that we put into the model. We denote it by the symbol gamma. This diagram represents the deformation in our model where the top was displaced towards the right. As you can see, the displacement is directly proportional to the shear strain. According to Hooke's law, if this strain is elastic, which it is proportional to the shear stress tau required to cause the deformation. We can conclude from this that a much larger shear stress is required to cause slip in a dislocation-free crystal compared with that required in a crystal containing a dislocation. This is borne out in practice. For example, here. Small metal whisker crystals can be grown dislocation-free from the vapor, and they have strengths much greater than bulk samples of the same metal, which contain dislocations. Here is the stress-strain curve for a whisker crystal of pure copper. Initially, the graph rises linearly, obeying Hooke's law, up to very high stress levels approaching 1 giganewton per square meter. This is some 100 times higher than the strength of a bulk single crystal. Suddenly, at this point of maximum stress, a dislocation is nucleated. It moves very rapidly, reading as it does so, and the strength of the whisker falls to about 1/10 of its maximum value. So how do we strengthen crystalline materials? By removing all the dislocations? No, we can only do that in microscopic samples, such as whiskers. We can't remove all the dislocations from bulk materials. In order to strengthen bulk materials, we need to obstruct dislocations, not eliminate them. To understand how we can obstruct dislocations, we need to understand the stresses and strains associated with them. And this model will enable us to do just that. It looks quite complicated, but it's actually very simple. It consists of a monochromatic light source here. In this case, it's a low-pressure sodium vapor lamp. In front of that, we have a polarizing filter. We put our model of a dislocation in here, and in front of that is a second polarizing filter. You may be surprised to see that this is our model of a dislocation. It consists of a sheet of epoxy resin into which we've drilled a central hole. From that hole, we've machined a narrow slit to the edge of the sheet. We're going to represent inserting an extra half plane of atoms by inserting this shim into the photoelastic sheet. The model is now dislocated. I'll just remove that shim and we'll insert the undislocated model between the two polarizing filters. Without a shim inserted, there's no effect because we're not putting any strain on the epoxy. Let's see what happens when the shim is inserted. The model now represents a crystal which has been dislocated. The shim here represents the extra half plane of atoms that we've inserted. Immediately, this pattern of optical fringes is formed. It approximates to two sets of nesting circular fringes on either side of the dislocation here. The size, shape, and location of these fringes can be interpreted to give the states of the stress and strain around an edge dislocation. Each fringe is a stress contour line. The maximum shear stress at any point on a fringe is the same. In stepping from one fringe to a neighbour, the value of the maximum shear stress goes up by a fixed amount, tau naught, which depends on the model material and its thickness. We can label each fringe with a whole number n from 1 upwards. The stress associated with any fringe is simply n tau naught. Looking at the fringes, we see that the shear strains are highest at either side of the dislocation. Beneath the dislocation, there's virtually no shear strain indicated. If we superimpose the familiar diagram of atomic positions, you can see this clearly. Below the core, the crystal remains cubic, whereas either side of the dislocation, the cubes have become distorted. We can use our apparatus to see how the stress varies around a dislocation, and we can relate that to the size of the Burgers vector of the dislocation. In our model, the size of the Burgers vector is related to the size of the shim that we insert into the photoelastic sheet. And we're going to see what happens when we change that Burgers vector, that is to say, change the size of the shim. And we're going to start with the smallest. We see that the number of fringes in the model increases with the size of shim used, and that the outermost fringe, that with n equal to 1, covers an increasing area. If we select a place with fixed coordinates relative to the center of the dislocation, and we measure the stress at that place in each model by counting fringes, we can plot a graph of stress versus shim size like this. It is linear, so we conclude that the stress and strain is directly proportional to the Burgers vector of the dislocation. Since the strain energy per unit volume at any place depends on the product of stress and strain, it follows that since both stress and strain are proportional to the Burgers vector B, the strain energy of a dislocation must be proportional to B squared. We can use a similar model to represent a pair of dislocations of equal and opposite Burgers vector. Here's our model. It's a similar epoxy sheet, a photoelastic epoxy sheet, and this time we've inserted a second shim from the bottom as well as our shim from the top. Let's see what happens when we put that between our two polarizing filters. Notice that the pattern of fringes around each dislocation is not the same as that seen previously. The presence of the second dislocation grossly distorts the fringes associated with the first dislocation. This is because the stress and strain fields of each dislocation interact. In general, dislocations will either attract or repel one another. They attract if by coming closer together their total strain energy will be diminished, and they repel if the reverse would be the case. This interaction between the stress fields is the reason why dislocations can act as obstacles to other dislocations, and that is the basis of work hardening. Precipitates too can act as obstacles to dislocations, and we have another model to represent that situation. As well as our dislocation represented by this shim here, we've drilled a hole into our photoelastic sheet of epoxy resin, and into that hole we've hammered an oversized peg, and that represents our precipitate. Let's see what happens when we put this model between our polarizing filters. This is the peg representing the precipitate. Again, the dislocation fringes are affected, showing there is interaction. This is the basis of precipitation hardening, a very important strategy for hardening engineering alloys. So what have we seen so far? We've looked at a model of an edge dislocation and seen that its movement is rather like a ripple moving along an atomic plane. We've also looked at a photoelastic model of edge dislocations. We've seen that the stress and the strain are both proportional to the Burgers vector of the dislocation B. Therefore, the energy of the dislocation is proportional to B squared. Finally, we've seen that the stress field of a dislocation is modified by the presence of another dislocation or a precipitate. This interaction leads to the dislocation or the precipitate acting as an obstacle to the movement of the first dislocation. In general, the interaction between stress fields will either lead to an attractive force on a dislocation or a repulsive force, and you might have thought that on average the two forces would cancel out. But there's a flaw in this argument. To see the flaw, let's consider how the potential energy of a dislocation might vary with its position when it interacts with a jungle of stress fields. We'll represent the interaction, that is the potential energy, by contour lines like those on a map. The lines form a landscape of hills and valleys, the details of which depend on the nature of the jungle. First, consider a straight dislocation draped across the landscape. The force acting on any part of it, such as here, depends on the slope of the hill measured at right angles to the dislocation. As you can see, in some places the force acts to the left, and in other places it acts to the right. In a random jungle, the forces on a straight dislocation would indeed cancel out. But why should the dislocation remain straight? A dislocation is flexible, so it can reduce its potential energy by moving downhill towards the bottom of the valleys. However, if it does this, the dislocation gets longer, which costs energy, so the final shape adopted by the dislocation is a compromise, which minimizes the total energy, potential plus dislocation energy. This compromise takes the dislocation near to, rather than along, the valley floors. Now you can see that any large-scale movement of the dislocation will involve climbing out of the valleys. That is, it will require extra energy and stress to move the dislocation. We conclude then that due to the flexibility of a dislocation, other strain fields always act as obstacles, and this fact accounts for work hardening and precipitation hardening. Earlier, we saw a dislocation moving in a two-dimensional model. Now let's consider some of the ways in which the length of a dislocation line moves in 3 dimensions. Let's consider glide in more detail by returning to our picture of a dislocation. You will recall that this type of dislocation, located at the edge of an extra half-plane of atoms, is an edge dislocation. Its Burger's vector is perpendicular to the dislocation line. The dislocation is able, under an applied shear stress, to glide in the plane which contains itself and its Burger's vector. This is the slip plane. If we apply sufficient shear stress, the dislocations glide, as we can see here. What happens if we introduce obstacles into the path of a dislocation? Obstacles to dislocations are any form of irregularity in the crystal structure, like a precipitate, or indeed another dislocation. Here we see a dislocation encountering 2 obstacles. In order to pass the obstacles by gliding, the dislocation must bow between the precipitates until the bowed portions have bent sufficiently to rejoin at the other side of the precipitates. For the dislocation to do this, it has had to increase its length. We know that the dislocation has a certain energy per unit length, so for the dislocation to pass the obstacles, we have had to put extra energy into the material by applying an increased shear stress. Glide isn't the only way in which dislocations can move. At high temperatures, dislocations can climb. As you will have read, climb is caused by the diffusion of vacancies, and this is only a significant effect at high temperatures. When an edge dislocation climbs, it moves at 90 degrees to its slip plane. This provides another means by which dislocations can overcome obstacles. The dislocation can be imagined to glide up to an obstacle, then climb above it, then carry on gliding on a higher slip plane. Climb occurs only in edge dislocations, but there is another form of dislocation movement which only applies to screw dislocations. This is cross-slip. You will recall that the slip plane for a dislocation is that plane which contains the line of the dislocation and its Burger's vector. The Burger's vector for a screw dislocation is parallel to the dislocation line, which means that there is an infinite number of possible slip planes. In fact, there are certain preferred slip planes, namely planes in which the atomic packing is closest. However, there are still several possible slip planes for a screw dislocation. Cross-slip is the name given to the phenomenon of a screw dislocation gliding in one plane, switching to gliding into another. It is likely to do this if it comes across an obstacle which can be avoided by gliding in a different plane. We see here a screw dislocation gliding towards an obstacle. When it's close to the obstacle, it cross-slips into a different plane and continues to glide. It may then cross-slip again, back into a plane parallel to the first, and carry on gliding. So cross-slip represents another means by which dislocations can pass obstacles in their path. So far, we have talked about dislocations gliding through a material as though there were an infinite supply of them. But where do they come from? Under a sufficiently high stress, dislocations can breed. There are several possible mechanisms by which they can breed, but we are going to look at just one. We start by considering a dislocation having a short length lying in the shaded plane pinned at the points A and B. It may be pinned at these points by intersecting dislocations. If we apply a shear stress to this dislocation, it can bow between the two pinned points until it has bent around sufficiently to send two new dislocations gliding away from itself in opposite directions. The whole process is able to repeat itself indefinitely, and so we have a source of dislocations. So far, we have looked at some of the properties of dislocations and how dislocations can move in a material, giving rise to plastic deformation. But how do we know that they really exist? Where is our evidence for the presence of dislocations? It is to the credit of early material scientists that they postulated the presence of dislocations as a medium for deformation of materials before there was any real firm experimental evidence. Since the mid-1950s, though, the transmission electron microscope has been commonly available as a means of examining dislocations and other fine-scale features of materials. The use of this instrument has enabled us to confirm many of the early hypotheses of dislocations and enabled us to refine greatly our theories of how they operate. Let's finish off by looking at some electron microscope images of moving dislocations. These pictures are taken from various metal samples. Notice the dislocations appear as dark lines against a light background. By applying a stress to the material, we can see how dislocations glide. For this to happen, the applied stress must exceed the yield stress, which is the stress required to cause plastic deformation. Next time you bend a paperclip, remember that similar dislocation movements are happening inside.